Look at the world around us, and you'll notice a slow, relentless breakdown. Left alone, almost every physical object eventually degrades. We see it in our infrastructure. A copper pipe that starts as a bright, reflective metal will gradually develop a dark patina, a process that steadily weakens the surface over years of exposure. We also see it in our food. A fresh potato chip left in the open air will turn soft, darken, and spoil in just a few days. At a glance, a metal pipe and a potato chip have nothing in common. But the tarnish on the plumbing and the rot on the food are driven by the exact same microscopic mechanism. To protect everything from our bridges to our food supply, we have to look past the surface and isolate the invisible chemical transaction taking place. We can observe this transaction by zooming down to the molecular level, using a controlled example, heating raw copper powder in the open air. This process is called oxidation. Copper molecules, 2Cu, bond with oxygen atoms, O2, from the air, forming copper oxide. This molecular change has visible consequences. The copper transforms from a brown powder into a coarse black coating. However, chemistry operates on a rigid ledger. Matter cannot be created out of nothing or destroyed. If the copper gained oxygen atoms, it had to take them from somewhere else. Oxidation is only one half of the transaction. The necessary counterpart to oxidation is reduction, the process where a substance loses its oxygen atoms. Because the chemical ledger must always balance, oxidation and reduction cannot happen in isolation. They are twin processes that must occur at the same time. Chemists call this dual process a redox reaction. The reduction pathway tracks where oxygen is lost, while oxidation tracks where it is gained. Elements swap positions, breaking original bonds to create entirely new substances. A redox reaction functions as a strict accounting system. It ensures that every single atom is tracked and accounted for as physical matter transforms. Returning to the macro scale, the mechanics of these atomic trades become visible in the specific ways our world breaks down. When metal infrastructure degrades, we call it corrosion. This is simply the slow oxidation of metals as they react with the moisture and oxygen in their environment. When food spoils, we call it rancidity. It is the exact same oxidation process, but instead of metal, the oxygen bonds with the fats and oils inside the food. By identifying how this trade works, we can intervene. When we paint steel or galvanize iron with zinc, we are creating a physical blockade that prevents oxygen from reaching the surface of the metal. We apply the same logic to our food, by flushing chip bags with nitrogen to displace oxygen, or by adding antioxidants. We deprive the fats of the atoms they need to react and rot. By understanding the requirements of these reactions, we move from being passive observers of decay to engineers of the chemical blockades required to stop it.